All right, looking at Bernoulli trials. So Bernoulli trial is a discrete random variable where the probability of success equals P and the probability of failure is 1 minus P. Each trial is independent of the previous trial. So I think the best way to explain this is with an example. And Mr. McDesmos is back and it's golf related. So let's have a look. On each hole, Mr. McDesmos either hits the green in regulation, we're going to call that a 0, or he does not. We call that a 1. Part of the probability distribution is shown below. Find the probability that he does not hit the green in regulation. So here's our probability distribution. Let me just go on a bit of a tangent here so you know what green in regulation means. On a par 3 in golf, par 3 means you've got 3 shots to get it in the hole. So you should hit the green on the first shot. So you've got 1 shot to hit the green in regulation. On a par 4, you've got 4 shots to get it in the hole. So you should hit the green on your second shot. And on a par 5, you should hit the ball in the hole with 5 shots. So you should hit the green on your third shot. So you either hit the green in regulation or you don't. It's what we call a binary variable. It either happens or it doesn't. So this is the probability distribution here. So what's the probability that I do not hit the green in regulation? Well, we can see that the probability that I do hit the green in regulation, I mean Mr. McDesmos, is 11 on 20. So X, that's when X equals 0, because we said hitting the green in regulation, we're going to call 0. So 11 on 20. So just over 50% chance of hitting the green in regulation. So given that it has to happen or it doesn't, I encourage you to think about what the probability of not hitting the green will be. And I'm hoping you would agree that it has to be 9 on 20 because the probability of success is 11 on 20. So the probability of failure is 1 minus 11 on 20, which is 9 on 20. So that's for X equals 1. Now, again, I just want to explain this part here, the probability that capital X equals X. Remember, capital X is our discrete random variable. Go back and watch the previous video to get more of an understanding of that. We're saying, okay, our discrete random variable is going to take on 2 different numbers in this case, 0 and 1. And 0 and 1 represent different events in the sample space. Again, either hitting the green in regulation or not hitting the green in regulation. So a discrete random variable takes on different values of X, 0 and 1 in this case. So let's talk about this last part as well. Each trial is independent of the previous trial. So in the golf analogy, we would say that Mr. McDesmos's performance on any hole is independent on his performance on the previous hole. And I encourage you to think about that, whether that would be true in the real world. Some might say that if you're playing particularly well, then the events wouldn't be independent. If you hit the green on regulation on the previous hole, maybe that makes you more likely, or it changes the probability that you hit the green in regulation on the next hole. However, one of the assumptions of Bernoulli trials is that the trials are independent. So the outcome on the first event, say, does not affect the outcome on the second event, which is probably not an unreasonable assumption in the game of golf anyway. So hopefully that makes sense. And good luck with your studies. What we're going to do next, I'll just mention, is you're going to put a bunch of Bernoulli trials together. And that's when you get what's called the binomial distribution. So we'll talk about that in another video. But that is what a Bernoulli trial is. Hopefully not too challenging of an idea. Good luck.